Why is water important to biology? What is unique about Earth compared to what we know about the other planets? We only need to look at Earth from this perspective to get an idea. Earth is the only planet we know of that sustains life, or at least life as we understand it. So what makes life as we know it possible on Earth? Water. Approximately 70% of the Earth is covered by water. The majority of the contents of a cell is water. The environment around most cells is water. All living things take in water. Many things live in and around water. And water plays an important role in allowing for reproduction. So why is water important to biology? Well, there's no life as we know it without water. So let's take a look at the chemical nature of water. Water, H2O. If we look at it structurally, we have one oxygen molecule bound to two hydrogen molecules. Now I could have drawn that like this, but that's not what water looks like. Water isn't shaped linearly. Water is bent. And this bent shape is very important to the chemical properties of water. Let's see why. If we look at this bond and remind ourselves that this chemical bond actually represents a pair of shared electrons. These two electrons are shared between the oxygen molecule, the oxygen atom, and the hydrogen atom. However, it's not necessary that these electrons are shared equally. I want you to think about if you had to share something with an older sibling. For example, me and my sister growing up for a little while shared a car. She's 2 years older than me. Who do you think got to use that car more often? And that's right, she did. In this case, oxygen is the big sister, and these two electrons are going to spend more time around the oxygen molecule than the hydrogen molecule. In chemistry, that's due to a property called electronegativity. Now, if these two molecules shared those electrons equally, then on average the electrons would spend their time right here in between. But since oxygen gets those electrons more often, then these two negatively charged electrons spend more of their time on this end of that bond. And so that this covalent bond is polarized. The electrons spend more of their time over here, giving this side of the bond a negative end, and this side a positive end. And we call this a polar covalent bond. Well, the same thing's going to happen over here on this one, so that this side of this bond is negative and this side's positive. So that if we looked at the water molecule in total and we divide it, we looked at it halfway through the molecule, that this half of the molecule is much more negative than this side of the molecule. And so not only is this right here a polar bond, but this molecule is a polar molecule. It has a negative end and a positive end. Water is polar. Now let's think about what that means when we have more than one molecule. If we have a bunch of water molecules together, they're going to orient themselves in a way that the positive ends of some of the molecules are going to be near the negative ends of the others. You see that here. And this attraction between the positive and negative end, these attractions that set up are not strong attractions. They're actually very weak attractions, but there are very, very many of them. And we call these weak attractions between these two parts of these two molecules a hydrogen bond. Hydrogen bonds are these weak attractions between or within parts of a molecule that are already in polar bonds. The polarity of water leads to hydrogen bonding, and it's this hydrogen bonding that's going to lead to all the other, or many of the other properties of water that we're about to look at. Now let's look at the physical properties of water. Water's sticky. What do we mean by that? Well, water's cohesive. It means water molecules stick to each other. Why? Well, we only have to look back here to see that. These hydrogen bonds cause these water molecules to stick together. Water is also adhesive, means it sticks to other things. I like to think about water molecules like individual balls. Maybe like the balls you jump into at a playground at a fast food restaurant, all the multicolored balls. Except imagine that each of those balls is a molecule of water, and they're wrapped on the outside with Velcro, so they stick to each other. Water's sticky. That Velcro is those hydrogen bonds. Each one of them is not strong, but if you have a giant pool of them with billions and billions of molecules, that's billions and billions and trillions of individual hydrogen bonds. Here we can see beads of water sticking to each other. They add the cohesion effect. And if we scroll down, we can see these water molecules sticking to these, looks like pine needles there. We can see the adhesion, that they're holding on and sticking to those surfaces. Now, what does this mean for living things? Well, this allows water to move up narrow tubes against gravity in what we call the capillary action. And if it weren't for this capillary action, we wouldn't be able to draw water up through plants like we can so efficiently. If it weren't for the stickiness of water, we wouldn't be able to use a straw to drink our soda. This stickiness of water also gives rise to surface tension. We can see this bug here walking on the top of this water and not falling through because these water molecules stick to each other because of the hydrogen bonding. Water is also a good temperature stabilizer. It has a high specific heat, meaning it takes a lot of heat to change the temperature of a large body of water. In fact, we define 1 calorie as the amount of energy it takes to raise 1 gram of water by 1 degree Celsius. So what does that mean? If I have 2 bodies of water, let's say a cup of water, and I have a pool of water, and they're both at the same temperature, let's say 20 degrees Celsius, and I add to these 2 bodies of water the same amount of heat. So let's say this is 100 grams of water, and over here I have 10,000 grams of water, and to each of these bodies of water I add the same amount of heat, energy, 42 joules, about 10 calories. What's going to happen to the change in temperature in these 2 bodies of water? Well, certainly the change in temperature here is going to be much, much greater than the change in temperature here. In fact, we may not notice any change in temperature here. It would be so small. Why is that important? Well, if our bodies are mostly made of water, it means our body temperatures don't change too quickly with the input on heat. And also, animals that live in and around water, the bodies of water that they live in, the temperature is relatively stable, which is important for metabolic processes. Living things have a fairly narrow range of temperature in which they work optimally, so water being a good temperature stabilizer is good for living systems. We also know that water has a cooling effect. As it evaporates, it takes heat away, which is employed by lots of living things to help them stay cool also. Another interesting physical characteristic about water is that ice floats. Now, why is that interesting? Most substances, as they turn from liquid to solids, become more dense, and the molecules of water do become more dense as they cool. But as they reach the point at which they start to crystallize, the molecules actually spread out a little bit for the shape of the ice crystal, such that the solid ice is slightly less dense than just less than solid ice, and so ice floats. So what does that mean for living things? Here's a lake covered by ice, and if we go underneath the water, we can see what it means is that this area below here, we have lots of living things, are actually protected. The air up here can get much, much lower than 0 degrees Celsius, but underneath the water it can't. This sheet of ice acts as a blanket insulating the area below, so that every time the water gets cold, it freezes, and the air temperature could be below 0, but the temperature of the water is not going to get as cold. If the ice sank and it filled up with ice from the bottom up, pushing the water higher and higher, the lake could easily freeze solid. But most large bodies of water will not freeze solid. Let's talk about solutions. Solutions are made of 2 parts, the solute and the solvent. In an aqueous solution, it has water as the solvent. It turns out that water is a very good solvent. In fact, we call it the universal solvent. It dissolves other polar substances well, and it also dissolves ionic substances very well. Let's look at why that might be. If we look at an ionic substance like salt, NaCl, When we put it into an aqueous solution, it splits apart into its member ions, Na plus and Cl minus. And because of the polar nature of water with its negative side and its positive side, it can surround these ions, in this case it would put its positive side this direction, negative sides, in what we call spheres of hydration, and surround each of the component ions, so it dissolves very well. But what types of things would not dissolve well in water? Well, nonpolar substances do not dissolve well in water. Let's finish up with a little talk about acids, bases, and buffers. You might say, why do we talk about acids, bases, and buffers when we're talking about properties of water? Well, let's look at a water molecule one more time. Water, which again is H2O, can be split up into an H plus and an OH minus, a hydrogen ion and a hydroxide ion. And if we think about what a hydrogen ion is, if we start with a hydrogen atom is one proton and one electron. That's the atom, and to make it an ion, it's a positive charged ion, so it must lose the electron. So to go from H to H plus, we have to lose the electron, and all we're left with is a proton. So a hydrogen ion is a proton. Here's a quick quiz for you. What's the pH of water? We use pH to measure the acidity or basicity of a solution. And what's the pH of water? Right? Water's neutral. It has just as many hydrogen ions as hydroxide ions, so you might think the pH should be 0, but in fact the pH is 7. Well, what does that mean? Well, let's look at a definition of acids and bases. An acid is any substance that when placed in water releases hydrogen ions, which we said were just protons. So sometimes we say that they are proton donors, H plus ions. Bases are any substance that when placed in water release hydroxide ions, which is not completely all the way true, but we could also define them as proton acceptors, which is always true. And buffers then are substances that can act as either acids or bases that help stabilize the pH so it doesn't change very much. So how do we measure it? What's the scale we use? We say it's pH, which stands for potential hydrogen. So if we know that acids give off hydrogen when placed in water, then we'd expect that acids would have a high pH. But when we look at the pH scale, we see that it goes from near 0, not actually 0, but near 0, which are the acids, and above 7 are the bases, so 7's neutral. Well, this gets me a little bit, because if potential hydrogen is what we're measuring and acids give off hydrogen, why are they not the high end of the scale? To understand that, we need to understand a little bit about what this scale is actually measuring. What we're actually measuring is the concentration of hydrogen ions in moles per liter. So if we have a number like this, these are the type of numbers we're dealing with. Very, very small numbers. And you try to build a scale out of numbers that look like this, it's just ugly. So we did a little math magic, and we decided that we can make this a much more pleasing looking number by, well, I'll show you. If we change these to scientific notation, it's a little better. So now we have a scale of 1 times 10 to the negative 1 through 1 times 10 to the negative 14, but that's still kind of an ugly scale. So let's do a little bit more mathematical magic. If I take the log of 10 to the negative 1, it gives me negative 1. Log of 10 to the negative 2, of negative 3, negative 3, and you can see what's going on here, but this is a pretty good scale. It's getting to be better, but it's in the negative, and who wants a scale in the negative numbers? And so this is what we come up with. The negative log of the concentration of hydrogen ions equals the pH, which makes this the pH of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And so 14, even though it's a big number, bigger than 1, actually represents a much smaller number. 0.0000000000001 is a much smaller number than 1. And finally, what happens when we put an acid with a base? Well, the acid's going to break into its member ions, H plus, Cl minus, and the base is going to break into its member ions, in this case Na plus and OH negative. And how can we rearrange these? Well, if I take these two, put them together, I can make water. If I take these two and put them together, I can make NaCl. Anybody recognize what that is? I have water and a salt.